Hello everyone, we're the Artemis Roads team, and for the past 2 weeks we've been performing in-depth research on redesigning the VIPER.
Hi everybody, my name is Andrae. I am from Saratoga, CA, and I am planning to major in electrical engineering.
My name is Simarleen Kaur. I'm from Dallas, Texas, and I plan on majoring in mechanical engineering.
My name is Shana Ibatuan. I'm from Gardena, California, and I intend on majoring in computer science.
My name is Clement, and I'm from Houston. In the future, I want to be a computer engineer.
Hi, my name is Hsieh, and I'm a rising senior from Lake Oswego, Oregon, and I'm interested in pursuing electrical engineering.
Hi, my name is Yael. I am from Houston, Texas, and I plan to major in aerospace engineering.
Prior to creating the mission patch, we discussed many ideas that could symbolize the VIPER missions. These included adding ice or water, using a snake to wrap around the patch, incorporating past prototype ideas, placing constellations in the background, and using the shape of the Hermite crater, which is where we're going to land our rover. Later on, we decided to add our team name VIRM to the front of the rover, which is Latin for roads, and use colors that would give the mission power and significance. We fused these ideas into a patch, which we hope would stand out in its aesthetics and symbolism.
Our goal is to redesign the Artemis Roads Volatile Investigating Polar Exploration rover, known as the VIPER, focusing on optimizing the wheel design for detecting ice and water concentrations at the Hermite crater located in the moon's north pole. This aligns with NASA's goal to sustainably explore and inhabit the moon. Our team's collaborative approach involved extensive research and the exchange of ideas to tackle the challenges of designing a lunar rover. We began by setting our team goals and VIPER mission objective, focusing on enhancing rover performance in the Hermite crater. Next, we examined the current VIPER design to understand its strengths and limitations. We then researched potential improvements and identified the challenges. Throughout this process, we consulted with mentors and NASA engineers to gather valuable insights. Using this information, we designed a prototype incorporating our proposed improvements. Finally, a failure mode analysis was made upon our design to identify possible failure points and build its resiliency.
Artemis VIPER rover stands at 8 feet tall and measures 5 feet in both width and length. It moves at a speed of approximately 1/4 to half a mile per hour and is equipped with several scientific instruments, those being the neutron spectrometer system, the regolith and ISRO for exploring neutron, also known as the Trident system, the near-infrared volatile spectrometer system, and the mass spectrometer system for lunar operations. Powered by solar energy, VIPER communicates through NASA's Deep Space Network, maintaining a direct-to-Earth radio link that requires a clear view of Earth. Communication has a 60-second latency, and scientists use the rover's data and images to avoid obstacles and redirect its path as needed. The VIPER rover's wheels can race and pivot thanks to a sophisticated suspension system that allows each wheel to move independently. This capability enables the rover to adjust its height and orientation in order to maintain stability and traction on uneven lunar terrain. This ability to pivot helps VIPER maneuver around obstacles, while racing the wheels can help it overcome rocks and steep inclines. This flexibility enhances the rover's ability to explore diverse lunar landscape, ensuring it can reach and study scientifically important sites that are otherwise difficult to access. This also allows VIPER to traverse the unique lunar landscape and terrain without the worry of a malfunction or damage to the structural integrity of the rover, whether it be the rover itself or its wheels. In order to simulate the vertical movement of the wheel modules on the VIPER rover, we determined that we had to use a 4-bar lifting mechanism. But what is a 4-bar exactly? Well, a 4-bar lift is a simple mechanical system that is used to raise or lower objects. It consists of 4 bars connected in a quadrilateral shape, with one bar anchored to a vase and the other forming a movable parallelogram. As one of the bars is pushed or pulled, the entire structure moves in a coordinated manner, allowing for controlled vertical motion. We also decided that in order to be able to rotate the wheel, we would have to use a pivot system that could allow the wheel to rotate up to 35 degrees when rotating to either side. In this video, we demonstrate the Lego model we've made. We made this in order to be able to visualize the mechanisms used on the VIPER's wheel modules. This would also help us eventually when we decide to scale the model into a larger structure using VEX parts. What you see here is a scaled up version of the replica we made using Lego parts. However, now we're using VEX parts in order to mechanize the systems and be able to use motors to basically replicate the movements of the VIPER's wheel modules. By building a scale replica of the VIPER's wheel modules using VEX parts, we can have a hands-on understanding of the mechanical systems used and potential challenges of our wheel design. By motorizing these parts, we can observe how the wheel pivots and races in real time, allowing us to analyze the stresses and strains on various components. This process also helps identify weaknesses and areas for improvement, ensuring that our designed enhancements are both practical and robust for lunar conditions. Additionally, constructing the module creates an iterative design approach, where improvements can be tested and refined through direct experimentation. By replicating the wheels' movements and functionality, we can gain insights into the rover's mobility and stability on uneven lunar terrain.
To further the Artemis mission's end goal of creating a sustainable lunar base, a robust and easily replaceable wheel design is critical for effective moon exploration and habitation. In current and future expeditions to the moon, rovers need to be able to quickly and reliably traverse the lunar terrain for everything from transportation of humans and goods to scientific exploration to the depths of lunar craters. In order to effectively identify areas of improvement in current lunar wheel designs, we analyzed the existing wheels used on the moon from NASA.
We needed a method to compare the effectiveness and durability of various materials. We were fortunate enough to have a discussion with Becca Siegfried, a NASA flight director who introduced us to technology readiness levels, which indicate how thoroughly tested and ready technologies are for use in space. To aid our decision to use certain materials in improving the design for the VIPER, we used NASA's technology readiness levels, known as TLR. This scale, ranging from 1 to 9, assesses the maturity of a technology throughout its development.
First of all, we will be starting with Perseverance rover's wheels. Unlike the lunar surface, Perseverance was built to combat Mars' relatively rocky surface. It is 0.5 meters in diameter with 6 curved titanium spokes to provide better control over rough terrain and small straight treads across the circumference of the surface. These specific components allow the wheel to retain its low weight while keeping with the minimum requirements of Mars' environment. The materials, weight, and durability were important considerations during the design process, as well as the TRO rating. Because of these criteria, aluminum and titanium were selected due to their relatively low weight and high strength.
While talking to Mr. Adam Noakes, a lecturer at the University of Texas at Austin, one of the questions we had regarding wheel design was why wheels with mesh weren't used in the current VIPER. He explained that because the intended speed of the VIPER was a maximum of 0.5 miles per hour, there was no need for the compliant design the mesh offered, as it would be an unnecessary use of material in space. Additionally, Mr. Noakes introduced us to the superelastic tire. The following suggestions made on the superelastic tire were made by Dr. Rajiv Dwivedi, a PhD in mechanical engineering. The superelastic tire uses a woven shape memory alloy, nitinol, to create a tire that doesn't require air. Dr. Dwivedi made some suggestions to increase traction and reduce weight and material. But after researching more into these suggestions, we realized that while this design provided increased traction, speed, and was a compliant wheel, it was difficult to manufacture, which strayed from our objective of creating a sustainable design that could be used in future settlements on the lunar surface.
The latest revision of VIPER's wheels include many similarities and differences from Perseverance. Its size of 0.5 meters, aluminum build, and spokes mimic Perseverance's specifications. However, due to its use on the lunar surface, it has small shovel-like treads, which are better equipped for traveling through regolith and navigating rocky areas. It also features holes of varying sizes across its outer rim and treads, which may be useful to reduce weight and prevent buildup of various materials. The wheel itself is meant for low speeds of 0.8 kilometers per hour, using the rover's suspension for shock absorption. The goal for improving wheel design for the VIPER rover is to combine the successes of past wheels, incorporating features from the Curiosity and Perseverance rovers. With a wheel diameter of 0.5 meters, design will utilize lightweight and durable materials like aluminum and titanium to withstand the harsh lunar environment. Adjustments will be made to enhance mobility over the regolith, ensuring better traction and stability. The compliant wheel will be optimized for 3D printing, allowing for easy production and maintenance. These improvements aim to boost the rover's capability to navigate and explore the diverse and challenging lunar terrain.
After extensive finite element analysis in 12 unique iterations, we came up with the design you see here today. Utilizing a unibody design while leveraging the ductility of titanium, the wheel is able to absorb shock while traveling along the uneven lunar surface without the need for complex suspension systems. This is accomplished through built-in titanium leaf springs connecting the outer wheel to the center hub, which provide compliance. We extensively studied how the specific geometry and material of the wheel impacts the compliance properties under load, which will be shown in a later slide. A compliant wheel design is critical for higher speed travel along the lunar surface. By increasing contact time through our design, it then follows from Newton's second law of motion that the impulse force will decrease, effectively absorbing the impact into the wheel. This allows wheels to travel at a higher speed where large momentum changes are more frequent. This wheel would enable faster travel than currently possible with the VIPER's rigid wheel design. The wheel still preserves the lightweight and simple construction that made the existing design so reliable. Here you can see the wheel geometry up close. The overall wheel has a diameter of 0.5 meters and a width of 0.2 meters. We derived the specific geometry through finite element analysis to maximize the displacement under load while ensuring the wheel doesn't structurally fail. This primary innovation of the shape is the variable width of our leaf springs. The outer springs are thinner than the inner springs, which helps to create a favorable deformation to force profile. Furthermore, the shape is designed to create limits of deformation, ensuring that in the event of a high force on the wheels, they don't move past their limits of elastic deformation. You can see here that if the wheels deform too much, the springs will collide, preventing further deformation. These features all help to create a compliant yet robust design that is able to absorb shock without risk of breaking. The intention of the wheel design is to be produced using metal 3D printing. The ideal technology for this wheel is selective laser melting, or SLM, which uses a powder metal stock, in this case titanium, melting it precisely with a laser layer by layer to build the part. This process is ideal as it produces extremely strong parts at nearly full density when compared to traditional manufacturing, while allowing for much more complex geometry not otherwise possible. As previously mentioned, we used extensive finite element analysis, or FEA, in the development of our wheel. Manufacturing multiple iterations would have taken too long and increased our iteration cycle too much. So FEA became an invaluable tool that enabled us to test and rank our designs with quantitative data rather than just theory. We used FEA to both analyze the geometry as well as material for the wheel. We primarily utilized Fusion 360's built-in FEA analysis, looking at the displacement as well as safety factor under static loads. Within Fusion 360, we determined that a minimum safety factor of 3 was acceptable. The safety factor is essentially just a number that determines how likely the part is to fail at any given point in the object under a certain load. Anything under 3 is considered dangerous and at risk of failure, so we set that as our minimum acceptable value at high loads. The use of Fusion 360's built-in FEA meant that we were able to quickly run simulations while altering designs, allowing for extremely quick iteration cycles when compared to other softwares.
To re-emphasize, our design goals sought a 3D printable, compliant wheel design to absorb impact better, increase traction, and traverse the lunar surface at higher speeds. So, the main design criteria is going to be to maximize the wheel's displacement or compression. Of a lesser importance but still a consideration is that the wheel should have minimal deformation at rest while maintaining its capability for large displacements. This ensures more efficient travel when the rover is moving at a constant speed with little momentum change. Shown here is our first prototype. We started by taking inspiration from existing unibody compliant wheels, which integrated a suspension system into the wheel through curved spring-like spokes. Our simulation revealed that the wheel was only able to achieve a maximum displacement of about 13 millimeters. Compared to the wheel diameter of 500 millimeters, there was less than 3% of deformation. A major reason for the lack of compliance is the thickness of the spokes, but the thickness was necessary for the wheel to withstand the weight of the rover. This leads us to our second prototype design. We increased the number of spokes and adjusted the shape to be thicker at points that were more likely to fail, and thinner at safe locations to increase the compliance. We designed this wheel to be optimized for 3D printing tests. Although it compressed relatively well at a small scale using plastic material, it did not scale up to metal. This wheel was only able to compress a maximum of 6 millimeters, or just about 1% of deformation. Our third major prototype was an optimized version of our first prototype, achieving a much greater compliance through thinning the metal and greater strength by increasing the amount of spokes. This wheel was able to achieve almost 49 millimeters of displacement, pushing us to a deformation of 10% of the wheel's diameter. Our final prototype utilized the information gained from previous iterations combined with a unique design to optimize for strength and displacement through the idea of integrating a layered design of spokes. The inside wheel has a larger width to increase the strength of the inner spokes that support the load from the rover onto the axle. The outer wheel spokes are much thinner to allow for greater compliance. With this design, we achieved 70 millimeters of displacement. The greatest amount of displacement we were able to attain at a safety factor of 3. This wheel design allows for deformation of almost 15% while maintaining a unibody design and 3D printability. Additional benefits of this wheel design include possible scalability by adding more layers to optimize for certain properties such as compliance or strength. To better inform our final conclusions, we collected simulation data in a spreadsheet and processed it in MATLAB. In total, we compared 3 materials: aluminum, steel, and titanium, and 6 different wheel shapes, including our prototypes, our final design, and the original VIPER and Perseverance wheels. Graphical analysis of the displacement of the different wheel shapes and the materials pointed to the best combination of design and material. To achieve our objective of finding the wheel that allows the greatest displacement, we set the safety factor to a constant of 3 and plotted the maximum load of the wheel against its maximum displacement. Although we would also like for the wheel to be strong and withstand more weight, compliance is the more important factor for us. Clustered in the bottom are the wheels with less compliant properties, such as the VIPER wheel, the Perseverance, and our early prototypes. Filtering out all the wheels with less than 5% deformation or 25 millimeters of displacement, we are left with the graph on the right. The VIPER and Perseverance wheel completely disappeared from the graph, which makes sense because they are rigid wheels that are not meant to be compliant. From the filtered graph, it is easy to tell that the final design has the most compliant properties. Next, we looked at our second objective of maintaining minimal deformation at a rest state of 174 newtons per wheel. Again, filtering out the non-compliant wheels, we are left with a clear graph on the right. The graph shows that the titanium versions of Prototype 3 and the final design best match this criteria, whereas the aluminum model remains too flexible. Though Prototype 3 has the least deformation at rest, the difference is minimal, and the final design has a greater safety factor, so overall, the final design has the most optimal properties. Finally, we analyzed the observed properties of each material from the simulation to determine the optimal material. To determine the average compliance of the three materials, we first processed the data in MATLAB, calculating the average displacement of each material at a safety factor of 3. Then we plotted it on the bar graph. From the graphs, it is revealed that titanium is the best option to optimize for compliance. We repeated a similar analysis for the average strength of each material by plotting the average maximum load at a safety factor of 3 in the bar graph. Unsurprisingly, steel is the strongest out of the three, then titanium, followed by aluminum, which is the weakest by far. We can conclude that of the three materials, aluminum is the least optimal, and although steel has the best properties for strength, it is not as compliant. More importantly, steel becomes brittle at low temperatures, becoming unsuitable for lunar exploration of the poles, where temperatures can reach as low as -249 Celsius. Thus, titanium is the optimal material. In addition, high concentrations of titanium are found on the lunar surface and can be harvested for 3D printing. When talking to Mr. Zebulon Scoville, the lead flight director for the Artemis missions, we learned that NASA is indeed planning to send a 3D printer to the moon and utilize the metals of iron and titanium on the moon to build habitats. This allows our wheel to be cheaply and sustainably produced for lunar rovers and transport on the moon.
Another crucial aspect of wheel design when traversing the lunar surface is the tread design. In order to effectively tackle the quicksand-like environment of permanently shattered craters, unique geometry is required. We decided on built-in treads much like the VIPER and Perseverance wheels, borrowing the shovel-like shape that was extensively tested on the VIPER rovers with the wavy pattern of the Perseverance treads. Due to the soft quicksand-like soil in the lunar surface, the shovel shape helps decrease sinkage, ensuring the rover does not get stuck. After talking to Rebecca Siegfried, who worked extensively on the Mars 2020 Perseverance rover, she explained how the triangular straight pattern on the Curiosity rover had issues with durability after years of use. The corners of the triangles created weak points that were susceptible to damage from the rocky surface. While the lunar surface is less rocky than the Martian surface, when traveling at high speeds, possible weak points in the wheels are necessary to limit. Furthermore, the wavy tread pattern is easily handled by the 3D printer, ensuring the unibody design while maintaining high traction across the regolith.
The main challenge faced by the lighting plus camera system is the environment it has to endure and the journey the rover has to travel to reach its destination. While the current design employs a lighting plus camera design in which the lights and cameras are attached separately, our modified design suggests a method of combining both systems to reduce the space occupied. The following combined design uses the original navcam design and adds a lighting system around the camera to ensure sufficient lighting in the camera view. The slight gap between the camera lens and the inside of the lighting ring ensures the camera can change focus while keeping the light in a stable position. Furthermore, we saw that the exposed ridges of the camera's length in the original design could be degraded by the lunar regolith, which is why our smooth and simple design, seen in Figure 3, prevents lunar regolith from obstructing the functionality of the instrument.
Operating in the extreme shadowed conditions of the Hermite crater presents a challenge for the VIPER mission. To address this, a thermal regulation system has been worked upon in collaboration between NASA and Advanced Cooling Technologies. The system includes loop heat pipes with integral control valves, which have a TLR of 7 for precise temperature management over long distances. External ammonia constant conductance heat pipes, which have a TLR of 8 for passive heat dissipation, and honeycomb radiator panels with embedded conductive heat pipes, which have a TLR of 6 for efficient heat radiation. These tools minimize power consumption and extend mission duration by reducing the required survival heat while ensuring the VIPER's hardware can withstand temperatures as low as -249 degrees Celsius without relying on active cooling. The new design will implement the system, which is already highly advanced and tailored to the specific challenges of the lunar environment.
One of the challenges that we faced during the early stages of our research was that we were having difficulties in finding the details from the previous rover wheel designs. With the help of Adam Noakes, a lecturer at the University of Texas at Austin, we were able to find various sources that directly applied to what we were looking for. One of the highlights of our team was that we were able to use our varying skill sets to contribute to the project. While some of our team members were better with hands-on work, others were better at researching and technological applications. Together, we were able to build on each other's ideas and create our final product.
Over the course of my time here, I've gained invaluable experience working with a like-minded team on real research. This experience has further strengthened my love for engineering and affirmed my desire to pursue a career in space exploration.
During my time in the SEAS program, I've had the opportunity to work extensively in a research environment, all while being able to collaborate with other like-minded individuals in an attempt to achieve the same goals. This experience has strengthened my goals in pursuing a career in aerospace engineering, as it will allow me to continue working on big projects in specialized teams.
Like many before me, I thought the SEAS program was vital in expanding my understanding in engineering. The lectures, assignments, and even long-distance experiences were beneficial in developing my future career.
During SEAS, I had the opportunity to use CAD software for the first time, and I was able to learn how to use my research abilities in the engineering design process.
The SEAS program has deepened my understanding of space exploration and earth sciences while honing my skills in research, problem solving, and teamwork. This opportunity has allowed me to even apply what I've learned to a real space mission.
From the SEAS program, I was introduced to new career pathways while also teaching me the priceless joys of working with a motivated team. The experience also furthered my resolve to pursue a research career in STEM to experience similar excitements.
Finally, we would like to thank everyone who contributed to developing, assisting, and enriching our research. These people include our mentor, Angaleta Crenshaw, Becca Siegfried, Brian Day, Parker Francis, Rajiv Dwivedi, Zebulon Scoville, and Selena Miller, and Margaret Baggio for directing the SEAS program.